Hello! In this video, we'll look under the hood of RISC-V assembly language to look at more about how jumps and pseudo-instructions work. So we've seen a variety of jumps in RISC-V, but actually if we look more deeply, the processor only supports two kinds of jump instructions, jump and link and jump and link register. Jump and link takes a 21-bit immediate that it adds to the program counter. That's a 2's complement number, so it could jump forward or backwards by up to 1,000,000. And it also takes a destination register of where to store PC plus 4 when we link. Jump and link register is similar, but instead of taking an offset to add to the program counter, it takes a source register and immediate. And it sets the PC to the source register plus the immediate, as well as linking the return address into RD. So those two jumps are actually enough to do everything. However, from the programmer's point of view, we don't always need all of that capability. So RISC-V defines things called pseudo-instructions. They're not real RISC-V instructions, but they can be more convenient for the programmer, and the assembler is going to convert them to real RISC-V instructions. So, for example, we've seen jump to some label, and that translates into a jump and link x0, comma, the label. So remember, x0 is register 0, it's hardwired to 0, so anything you write to it is just ignored. So jump and link, where we're putting the return address in register 0, we're just throwing away the return address, and that can be a simple jump. Remember, we also used a jump and link for a function call, and that's equivalent to jump and link RA, comma, the destination. So by default, JAL will put the return address in RA, unless we ask to put it in some different register. To return from a function call, we used jump register to RA. In general, we might jump register to any register, any source register, and that's equivalent to jump and link register x0, rs, 0. So that will put the return address in the 0 register, throw it away, and it will take the destination rs, add 0. So just rs directly. So jump register RA is actually a jump and link, JR to RA is really jump and link register 0, RA 0, to jump to what's in RA and throw away the return address. Finally, it's sometimes handy to use return instead of jump register RA, just as a way to return from a function, and those two are synonymous as well. So we see there are 4 different pseudo-instructions for jump from the 2 actual jump instructions, JAL and JALR. Next, let's talk about labels a little bit more. A label indicates where to jump to, and it's represented in the jump as an immediate offset, as the number of bytes past the jump instruction. So for example, if we were at 300 and we wanted to do a jump and link to simple, which was at 51C, the offset is 51C minus 300, which is 21C in hexadecimal. So jump and link simple is actually encoded as jump and link return address, comma, 21C, where the offset to jump by is the 21C. And these offsets are limited to 20 bits for a jump and link, or just to 12 bits for jump and link register, and this limits how far a program can jump. So there's a special instruction to help for jumping further called add upper immediate PC. It takes a destination register and a 20-bit immediate, and it sets RD is equal to the current PC plus this immediate in the upper 20 bits. So if we wanted to do a function call, let's have a pseudo instruction called call that takes a 32-bit offset. It's just like jump and link to immediate, but it allows a 32-bit offset instead of a 20-bit. So we can break it into two true instructions. First, add up or immediate PC, RA, comma, and then our 20-bit upper immediate, and then jump and link register RA, comma, the 12-bit lower immediate. So this will do the PC plus IMM 31 through 12 in the upper bits plus IMM 11 through 0 in the lower bits. So altogether add a 32-bit immediate. And it's using RA as a temporary variable here and here, but then it's linking to RA. So we'll put the return address in RA. So those were some examples of jump pseudo instructions. Jump to label is equivalent to jump and link 0, label. Throw away the return address. We saw jump register to RA was like a jump and link 0, RA, 0. Another handy instruction is move. So if we wanted to move S3 to T0, we could do that with the true instruction of add I, T5 gets S3 plus 0. But move is a little bit clearer of what we're doing. You've noticed there's no not instruction among the logical instructions in RISC-V, and the reason is that we can do it with an exclusive or immediate. If we wanted to invert T2 and put it in S7, we can XOR immediate T2 with -1, and put that in S7. Remember, -1 as a 2's complement number is 32 ones. And exclusing or something with a 1 inverts it. So we invert all the bits of T2 and put them into S7. A no-op is an instruction that does nothing, maybe if we just wanted to pass time. And we can do that with an add I of 0 gets 0 plus 0, do nothing. Suppose we wanted to load a 32-bit immediate. The LI instruction stands for load immediate, destination register, and then 32-bit immediate. And like we saw back in the immediate section, we can do that by breaking it into two steps. A load upper immediate with the upper 20 bits, and then an add I with the bottom 12 bits. You might have noticed that our instruction set only had branch less than or branch greater than or equal. So there's actually branch greater than, if we wanted to compare S1 to T3, branch greater than of S1 and T3 is the same as branch less than T3 S1, because if we just reverse the order, we switch less and greater. Sometimes we want to compare to 0, so a branch greater than or equal to 0 of T2 to a label L7 can be written as branch greater than or equal T2, 0 to label L7. So that would see if T2 is greater than or equal to 0. A little bit ago we mentioned the call function that does the add up or immediate and then jump and link register to handle a 32-bit offset in our function call. And then we'd also said return is a pseudo instruction for jump and link register R0, RA, 0. That just returns to RA.